Well, hello, Algebra 2 gang. You've already had some exposure, a couple of Desmos activities that expose you to function transformations, and you're about to do a delta math activity with some transformation basics. And before you do that, I'm here to give you a quick recap and I hope a little pep talk to get you started. So, as an example, if we had an equation, which I think you could probably graph, y equals x squared, you would be able to sketch a pretty good graph of that on an xy plane. You know that it has a vertex at the origin and follows some basic rules for movement. So we've got a vertex, have a point at 1, 1, 1, negative 1, or sorry, negative 1, 1, 2, 4, negative 2, 4, and so forth. And you'd have a graph that looks like this. So the other way we can talk about this is in terms of functions. We could say, okay, let's define f of x equals x squared. And these sort of superficially look like the same kind of equation. And so some people would say, well, this represents the y coordinate of the graph, but I prefer to think of it as the output or vertical position when you're thinking of graphing. Oops. And what goes into the function is it's the x, it's the input, and it represents the horizontal position. Okay, so now in the delta math activity, you might be presented with an example that is something like y equals x squared plus 3. And you need to modify the graph given to you to represent that new function or new equation or new relation, um, y equals x squared plus 3. And so the trick is to recognize that this is just the f of x function that we defined over here, and that we're taking the output of it, the y coordinate or the vertical position, and we're adding 3 to it. So what that means, we haven't changed the input at all. The input is still just x, but what comes out of the function is going to have 3 added to it. And in terms of graphing, that just means that we're going to take each of the points in the original graph and we're going to add 3 to their y coordinates. So we end up building an identical version of the parabola, point by point. I need to graph it better than that, point by point, where what's changed here is that we've translated the original parent function, this f of x equals x squared graph, we've translated it up 3 units. Other than that, it looks exactly the same as the original graph. Now, when you're doing this in delta math, you're going to be presented with a graph of a parent function that is the correct parent function for whatever equation you're looking at. So in this case, if you'd been given y equals x squared plus 3, they would include a graph of the x squared function. And your job would be to figure out how to move or translate that graph so that it corresponds to this new transformed function. So in that case, what you would see is somewhere on the graph, and usually at the origin, there'd be a green point. And all you need to do is drag that green point wherever it needs to go, and delta will redraw that original parent function exactly the way it was done before, except it's been moved somewhere else. So this is an example of a vertical translation. The next kind of translation you're going to see is a horizontal translation. And using the same parent function that I have right here, you might see this appearing as something like y equals, let's do x plus 3. Okay, so now look at this carefully, and do you see how this equation is different from this one? In this one, we've just taken the x squared that we had before in the parent function, and after that's been squared, we go and add the 3 to it. In this one, before we square the x, we add 3 to it. So it's not just the input to the function that's getting squared, it's the input plus 3 getting squared. So what does that mean? Well, let's think about this as a function transformation. Writing it in the function notation, I would be saying that this is f of x plus 3. So remember, f of the input, whereas everything inside the parentheses is the input to the function. We've defined f of x to say whatever the input is, whatever's inside the parentheses here, gets squared. Whatever is in the parentheses gets squared. Well, so now in this transformation, I'm saying, hey, let's give function f as an input, not just x, let's give it x plus 3. So this entire input needs to get squared. And that's what's happening in this equation over here. Everything inside these parentheses is being squared. And so that's the equivalent of saying f of parenthesis x plus 3 close parenthesis. Now notice another thing about this. Whereas over here we took the output of the function and we added 3. That was saying we're taking the y coordinates that come out of the function and we're adding 3. What comes out of this transformed function f of x plus 3, where the x plus 3 is in parentheses, what comes out of that function doesn't get modified at all. There's no plus or minus or multiplication, anything happening outside the function. And that means that the y-coordinates in our new transformed graph don't change. So if the y-coordinates of the graph don't change, what does change? Well, that would be the x-coordinates. So let's think about how that would work. If we look at this parent function here, the original y equals x squared function, the vertex happens at 0, 0. So our new transformed function is going to have a vertex also. And that vertex happens when the input to the function is 0. So we need to ask ourselves, when is the input to this function going to be 0? Another way of saying this is the vertex will happen when x plus 3 equals 0. This will be true when the input to the function is 0. Well, if we solve that equation, we get x equals negative 3. And that means that when x is equal to negative 3, we will find the vertex of our transformed function. So let me make a new plot for this. So when x is negative 3, x is negative 3, if we put negative 3 into this transformation, negative 3 plus 3 is 0, we're going to be finding the value, output value for f of 0. Well, when you give the function f 0 as an input, and this is our definition up here, when you give 0 for input, what you get out is 0 squared, you get 0. So that's why over here I've plotted this point at negative 3, 0, because in this transformation, when I use x equals negative 3, we're giving the function 0 and it gives me 0 as an output or a y coordinate. Now, if I went and gave the function, my transform function, um, different color, at, let's say, x equals negative 2, what happens? I'd be evaluating f of negative 2 plus 3, or f of 1. Now, f of 1, I already know what f of 1 does, because f of 1 is 1 squared, which is 1. And that point on the original x squared graph is right here. So in order to get that point on my transform graph, I had to put in x equals negative 2, because x equals negative 2, when I throw that in here, I'm evaluating f of negative 2 plus 3, which is f of 1, and f of 1 is 1. So going back to my graph, at x equals negative 2, I'm going to plot a point at y equals 1. And continuing with that thought, if I'm at, say, x equals negative 4, that means I'm evaluating f of negative 4 plus 3, which is f of negative 1. And f of negative 1, if I go back and look at my parent function here, f of negative 1 is an output of positive 1. So that means I can plot yet another point on my transform graph at negative 4, positive 1. So what you can see here is that I'm starting to develop the points for a parabola that have been shifted from where they normally are at the origin. We've translated them to the left by 3 units. So cool thing about this to notice is for the vertical transformation, if we had a plus 3 outside the parentheses, that gave us a vertical positive upward shift or translation. When I had plus 3 inside the parentheses, it caused a horizontal shift or translation, negative 3 to the left on the graph. So that's why people tend to think, things that happen inside the parentheses are sort of opposite of what you might expect. This plus 3 means that to get the origin or the vertex on my parabola, I need to have a negative 3 for x, and that means that the graph is shifted to the left. So then that, just to summarize, is a horizontal translation. All right. And the last little piece I want to mention is if you see something like a negative f of x, or I should say like negative x squared, what does that mean? Well, you're taking the output of the function, which is the y-coordinate, and you're making the negative. So in this case, you would end up with the parent function taking all the y-coordinates and plotting them as negative y-coordinates. And so you get this graph that's upside down. Or as we like to say in the business, this is a reflection over the x-axis. So it's like having a mirror image. So again, things that happen on the outside of the function, this is a negative on the outside, causes a reflection that's vertical or reflecting across the x-axis. If you had a transformation that was, say, f of negative x, where the negative is inside the parentheses, that causes a transformation that is a reflection over the y-axis. So you get a mirror image horizontally. For a parabola, that's not terribly interesting because they're symmetrical across the y-axis. But other functions, you would see that reflection over the y-axis. So I think you got enough information here to help you through the Delta Math activities. And remember, each Delta Math activity also has its own little video that you can look at.